It's Mr. San. I'm back again. I want to go through a couple warm-up problems and walk through problems in your text. So the first one I want to talk about is a warm-up problem for velocity versus time. Oh, this is, by the way, this is the topic 1 of Unit 2. And this problem is just a warm-up. I'll go through a different problem where you're finding the area underneath a velocity versus time curve and kind of talk you through that one a little bit more because I think I went through that one a little quick on the last video. So here we go. Let's tackle this problem. It says draw a velocity versus time graph given this position versus time graph and be sure to label the axes. So let's go through this. I use Blueberry to do this. I'm going to make my velocity versus time axis right here. I'm going to say this is the x-axis. I'm doing this freehand, which is kind of tricky, but you can do the same. This is going to be, oh, why did I do that? That's ridiculous. This is going to be velocity versus time. Velocity and time. Now, I see this is always a positive slope, so I know this is going to be always a positive velocity versus time graph, so I'm going to put the 0. I'm just going to put it way down here. And that's 0. I meant that to be right here. Yeah. Okay. And I'm just going to translate this straight down here as well as I can. So it's right about there is 0.1 seconds. And if you translate this straight down here, 0.2. This is 0.3 seconds. Okay. Now, how do you do this? How do you translate this into this in a real way instead of just going through the walkthroughs and kind of estimating? Well, you take a point, and this is a time point right here, so I'm going to use this time point, the slope at that point. You find the instantaneous velocity at that point, which also means the slope at that point. And since this tangent of this line right here is just going to be that same line, since it's not changing at all, I don't really need to make any more calculations besides just finding the slope of this line right here, since I know the velocity or the slope of this position versus time graph isn't changing. It's staying the same. The slope is the same. You could calculate the slope here, you could calculate the slope here, you could calculate the slope here. It would be the same for all of those points. It doesn't matter which one you calculate for and how many times you calculate the slope on this line, it's going to be the same. So let's just use this right here as a convenience point on the slope. So this is exactly, it looks like 20 centimeters. It goes up 20 centimeters and it goes over 0.1 second at this point right here. So rise is, so the slope here, let's just make this very clear. The slope equals the delta y over the delta x. And for us, that means the change in s over the change in time, which is, that's the formula for velocity, by the way. And in this case, this delta s is 20 centimeters. It's 20 centimeters minus 0, because this is the 0.0 centimeters right here. We could have chosen any point, but I chose this point right here to choose the change in displacement, 20 centimeters minus 0 centimeters over, and then look at the change in y here. This is going to be, the change in x here, which is also the change in time. That's 0.1 seconds. That's the final time, minus 0 seconds. This obviously is 20 centimeters over 0.1 seconds, and that equals 200 centimeters per second. Okay. Now, let's think about sig figs here. Well, it's not really that important because all we're doing right now is making a graph. So we just need to find a way in which we can represent 20 centimeters per second on the velocity versus time graph. So here's the seconds. That's the time, in other words. I should have written that down before. And the velocity, well, let's just, I don't know what we want to do here. We could say every 2 is 50 centimeters, if that makes you happy. Fantastic. That's 100 centimeters per second. And you go up another, what did I say that was? Oh, I should have done every 2. My bad. Let's just make this. Just make this 100 centimeters, and let's make it very easy on us. That's 200 centimeters per second. Notice how I'm kind of winging this, so to speak, to make my axes. As long as these are spread out evenly, and this would be 0 centimeters per second, they're equal intervals. I can name them whatever I want to name them. This one up here would be 300 centimeters per second. That's our velocity. And the velocity, again, would be in centimeters per second. So that's what this axis is, centimeters per second, and this is time. So at this time point, what is my velocity? Well, it just so happens to be at every single time point, 200 meters per second. I'm going to draw this in a different color. It looks like, so you'd go to the time point that you wanted, and you'd say, it's 200 centimeters per second at that time point. What about at this time point? Well, it's the same slope over here, so it's the same velocity. So again, it's at 200 centimeters per second. Here, guess what? Same slope, same velocity. It is 200 centimeters per second. Doesn't matter what point you choose along here, it's always going to be 200 centimeters per second, because this slope is the same the entire way. So if you look at this, I can't draw a straight line. I just want to draw a straight line so badly. If I could only just draw a straight line. There we go. Somewhat straight. That's going to be our velocity versus time graph based off of this problem right here. Got it? Great. Let's take a look now at another problem where you have to find the area underneath a curve. This is problem number 5 in your practice problems. So like we said before, the velocity is change in position over change in time. So if you want to get the change in position by itself, which is also known as the displacement, you take velocity times delta t. This question right here says calculate the displacement of Robin after 10 seconds using the chart or using the graph below. Show your work. So to know this person's displacement, you need to find v times delta t over this entire time span here. Well, v times delta t, this whole axis is v, that's the velocity. So velocity times delta t right here is going to be this axis times this axis. That turns out to be this area under the curve. That's not as easy to see as a different time point. I'm going to choose this time span right here. So I'm going to go back to that little triangle in a second. But for right now, this goes off a little bit more. That just makes it a little bit more tricky. This darn problem. But it just says to 10 seconds. So let's just go to 10 seconds. Okay, so to 10 seconds. So from this time span right here, it's a little bit easier to see. Let's say that you want to find the displacement, how far something's gone, if it's been traveling at 2 meters per second over this time span right here. So from 4 seconds to 10 seconds. Well, to figure that out, you would just multiply the velocity, since it's the same velocity that's traveling over that time. You would say that's 2 meters per second. I'm just using this equation right here. Times the change in time. So it's going to be 10 minus 10 seconds minus 4 seconds. That'll give us our change in displacement. So this is going to be 2 times 6, which is 12 meters. That's our delta S. That should make sense to you. How this equation works, it'll get you this answer right here. Now I want to look at this graph and see something that's really cool. And that is, if you look at the area underneath this graph right here, you can calculate what this area is on the graph. So now let's just put the ideas of velocity and time out of our mind and just look at this area under the graph here and just look at the numbers. There's 2, this goes up to 2, and this goes from 4 to 10. That's what those units are. So that means that there are 6 units right here, and this is 2. So 2, if you want to find the area of this under this little rectangle underneath this box right here, it's 2 times 6, and that's 12. Well, that's what our displacement was. So if you find the area under a curve in a velocity versus time graph, you find the displacement. It's an awesome little trick. If you have a negative area under a curve, well then the area that's, I'll use a different color for that. I'll use blue. The area under this curve right here, that's a negative area then. So this would be a negative displacement. Now you can find the area of this little triangle right here fairly easy. It's just the way that we normally find an area of a triangle, which is 1/2 base times height. We're using geometry again to solve this problem. And then you've got this little triangle right here, so this is going to be a negative number, and this is going to be a positive number right here. But we can find the area of both of them by using this little equation, 1/2 base times height. Let's find this area right here. So 1/2 base, the base is going to be 2 seconds, and the height is going to be -2 times -2 meters per second. Look at our units. Our units, these seconds are going to cancel out. And this is going to simplify. This is going to be 1/2 times 2 is 1 times -2, and this is going to be a -2 meters. So that's what the area of this little triangle is over here. This triangle over here, let's use a different color. Let's use spring for this color. So this area right here, I'll use 1/2 base times height for this one. So in this case, 1/2 base would be 2 seconds, because it's going from 2 to 4. That's going to be 2 seconds times the height, which is 2 seconds. I'm sorry, 2 meters per second. Again, our seconds cancel out. Okay, our seconds cancel out, and we're going to get as an answer here, we're going to get 2 meters. So we've got 2 meters, minus 2 meters, and 12 meters. If you add all of these areas together, that shows you the total displacement that this thing, or Robin, has traveled. So that's Robin's displacement. So 2 plus 12 minus 2 equals 12 meters. That's Robin's displacement. I hope that makes sense. Should make sense. Good luck.